For part 4 of Notes 11, I'm going to go through example B and then just sort of wrap up and transition us into what's next now that we've been able to check these assumptions in sort of a better way than we've done in the past. So we're going to use the bird data from activity 4C. And what we want is, first we want to just find the variances for each sample. So we're essentially going to check the equality of variances the way that we've done in the past. So I'm going to go to SAS here, and I've got the data from 4C, and I need to fill in a couple pieces. So I'll call my data set birds. I need to add a $ because status is qualitative. I need to add the word cards here. And I'm just going to get rid of this stuff because that's not what we're doing right now. But I will add proc t-test data equals birds. And actually, let me do proc univariate because we want the variance here. So proc univariate data equals birds. I want to compare my two groups. So they're called, they're in the status variable. That's my qualitative variable. And my other variable is called humerus. That was the length of the bone. And run. And I'll just run everything here. And let's see, this is the group that perished, so the birds that died in the storm. And you can see that the variance is pretty small. It's 0.00055425. And so if I go back to the notes, you can see that I've got that here for the first one, 0.00055. And it looks like the second one should be 0.00039. Let's make sure that that's actually what we get. So I scroll down. Here's the birds that survived. And here's my variance of 0.00039. All right, so I found my variances for my two samples. I want to use these to decide if the variances for the population could reasonably be the same. So the first thing I might do is just compare them and see if one is double the other. And I could try to maybe take the smaller one and double that. So 0.00039 doubled would be 0.00078, I believe. That is bigger than this, and so it looks like neither is double the other. But the easier way to do it is to actually calculate this F value and just take the bigger sample variance divided by the smaller one, and I get 1.41. Since that's less than 2, that tells me that neither sample variance is double the other. So by our old method, this would be fine. We could go ahead and say the two population variances are reasonably equal. All right, but we might actually want to use our new method too. So we're going to use proc t-test, and we're going to use the equality of variances test that it gives us in the output to see how this assumption is. So now I'll go back to the code, and I'll start proc t-test, data equals, I called it birds, and I'm not doing the actual hypothesis test or confidence interval or anything like that yet, and so that's why I'm not bothering with the H0, sides, alpha, because I really just want this equality of variances output that it's going to give me. And again, I need to put class and status to specify that it's two independent samples, the birds that perished and the birds that survived. And I'm interested in the humerus variable, the length of that bone. And then I can put run. And I will run this code here. And you can see I've got a bunch of information I need to sort of sift through. But this section is the one that we're interested in right now, this one that says equality of variances. So it should look sort of like what you saw at the top of this page in the notes. Equality of variances. Don't worry too much about this. It's got some degrees of freedom that we'll come back to later in the semester. But I also get my test statistic and my p-value right here. So if I go back here, this should match the 1.41 that I calculated, and it tells me that the p-value here is about 0.36. So what that means, I've got a p-value bigger than 0.05, so I have insufficient evidence that the alternative hypothesis is true. And so if I just refresh my memory and I go back, the alternative said that the population variances are not equal. I do not have enough evidence to conclude that this is the case. So if I did have enough evidence, that would worry me. But since I don't, I'm going to feel okay assuming that the population variances are equal. And you can see if you scroll down here, that's what we said, is that since there's not enough evidence to conclude the variances are different, it at least seems okay to assume that they're the same. And so in this case, our new method and our old method, they're both giving us the same answer. It's not always going to be the case, but it's nice to see that it's not like we were just completely making things up before. So now that we've talked about all three assumptions, you might wonder, well, what happens if we end up in a case, so unlike the birds data, but another example where it's not okay to assume that the population variances are equal, for example? What do we do in those cases? If the random samples assumption isn't met, we're really out of luck. So if we have data that's not from a random sample, and in that case then we don't think it's representative of our population, any sort of hypothesis tests and confidence intervals and things that we do are likely to be misleading, and there's nothing we can really do to fix this. We can't go back in time and change how our sample was gathered or anything like that. So we really do need a random sample to be able to do statistics the way that we've been learning. On the other hand, if either the normality assumption or the equal variances assumption, or even both of those assumptions, have not been met, so if we've decided that they're not actually appropriate, we don't just want to go ahead with our test statistic and our confidence interval and hypothesis test the way that we've learned, because our results would be misleading. But that doesn't mean that we're completely out of luck. What we can actually do in those cases is we can consider changing the scale of our data. And we call this transforming the data. And I think that a lot of times this maybe sounds like we're doing something we shouldn't. We're like messing with our data. But you can think of it sort of like, say I measured everybody's height in inches. I could transform it to centimeters. All I'm doing is changing the scale that I've measured on. I haven't actually changed the data. Nobody's height has actually changed. I'm just looking at it in a slightly different way. That's essentially what we're doing. Now, we're not going to go from inches to centimeters, but that's the basic idea. What we are going to use is something called the natural log transformation. And so we'll sort of brush up a little bit on what this is in Notes 12 and see how we can use it to help us in these cases where one or the other of these assumptions was deemed not reasonable.